is one of my favorite lectures of the semester, just because I think it's really interesting, and hopefully you do too. So really what we're focusing on, and it's the only video for this day of class, is limitations to VO2MAX. So we've got two outcomes for this lecture, both of them relating to VO2MAX. Okay, so when it comes to VO2MAX, there is a limit to what it can be. And as we've discussed a few times, it's affected by these three things. So we've got oxygen content, oxygen delivery, and oxygen utilization. Now, when it comes to these three characteristics, or these three categories, or however you want to describe them, there's three primary systems. You've got the muscular, the cardiovascular, and the respiratory. So let's talk about each of these. So with the respiratory system, remember the job of the respiratory system: get oxygen into the body, get CO2 out of the body. Now when it comes to VO2MAX, we're more concerned about oxygen as opposed to carbon dioxide. So we want to get as much oxygen into our body as possible. It's important to know that the respiratory system is rarely, if ever, the limiting factor. And this is why. At rest, as you're sitting here listening, watching, whatever you're doing, your minute ventilation, that's VE, is probably about 5 liters a minute. Okay. Now, when you get to max exercise, typical adult gets up to about 100 liters a minute. I actually have seen someone that got nearly 200 liters of air, was breathing nearly 200 liters of air per minute. This was a large individual, somebody that was a little bit bigger than me, a little bit so taller, bigger, more in shape, that sort of thing. What's really interesting though is that, and we've mentioned this I think last week, that even when we're at our VO2MAX, our respiratory system really isn't at its limit. You can do a protocol or do a test that's called maximal voluntary ventilation, and basically you just breathe as fast as you possibly can for a short period of time. And when people do this, they're usually 10-20% higher than what their minute ventilation is during maximal exercise. So it's really hard to tap out your respiratory system. So if we're going to simplify the math here, just think that your alveolar PO2, or your alveolar oxygen, is about 100 millimeters of mercury. So that translates to a fraction of inspired of oxygen of about 13%. So at rest, you're bringing in about 0.7 of a liter of oxygen per minute. And the way I got that is I just multiplied 5 liters times 0.132. It gives us about 0.7 of a liter. Now at maximal exercise, you're bringing in closer to 26.3 liters of oxygen per minute. That is a really high amount, and we come nowhere close to using all of that. I think the highest I've ever seen for VO2, absolute VO2, is 8, maybe 9, which is less than a third of 26. But it is possible that the respiratory system can limit VO2, and so there's two primary ways that this can happen. One is diffusion capacity, and the other is shunting. So when it comes to diffusion capacity, this is as a result of reduced transit time. So blood flow is moving so quickly that the red blood cell will travel through the pulmonary capillary in a manner that prevents it from equilibrating. So in other words, we can't get the oxygen from the respiratory system into the cardiovascular system. And so as a result, we don't get as much oxygen into the bloodstream, even though there is a huge amount of oxygen available. And then there's shunting. And so remember, shunting is where we have blood flow but no airflow. Okay, and so we've got blood that's bypassing pulmonary capillaries, and as a result, we have oxygen poor blood mixing with oxygen rich blood, ultimately reducing the overall oxygen content of what leaves your left ventricle. So next we've got the cardiovascular system. And so the job of the cardiovascular system with regards to VO2MAX is to get blood, but ultimately get oxygen to the muscles. The heart can increase its capacity by 4 to 8 times. So this says VE, I didn't change that. So this should actually be Q here. So we're going to cross this out. That's Q. Okay, and this is also Q. So that Q for cardiac output is about 5 liters of blood per minute. Man, I really got some typos here. So this is blood. All right. And at max, we can get up 20, and if you're an elite athlete, up to 40 liters of blood per minute. Okay, so that's still a significant increase, but it's nowhere near what the lungs have the capacity to do. So again, doing a little bit of math, when it comes to cardiovascular limitations, ultimately it's cardiac output. Just how much blood can you deliver? Your heart rate can only go so high, your stroke volume can only go so high, and your stroke volume and your heart rate are related. As heart rate goes up, filling time goes down, and that's ultimately going to reduce stroke volume, or at least limit it. So in theory, your maximal cardiac output is heart rate max times stroke volume max. So now we're getting into the more math. Normal oxygen, there's normally about 200 milliliters of oxygen per liter of blood in your body. That doesn't really change. And so when it comes to calculating delivery, we go oxygen delivery equals the amount of oxygen in your blood, so that 200 mils of oxygen per liter of blood times cardiac output. So at rest, this translates to about a liter of oxygen is delivered throughout your entire body per minute. At max exercise, depending on if you're a typical individual or an elite athlete, that's anywhere from 5 to 8 liters of oxygen per minute. Now again, this is just absolute, and it depends on size, and there's some other factors, but just to kind of give you a rough idea. And remember, if we can only deliver 8 liters of oxygen per minute, respiratory system, in theory, can deliver or can bring in about 25 liters of oxygen per minute. So respiratory very rarely is the limiting factor. Cardiovascular very often is. And then finally, we've got the muscular system. So the job of the muscular system is to actually get that oxygen out of the bloodstream into the muscle, and then get it to the muscle where it can be used to specific parts. And really, that's specifically the mitochondria. So within the muscular system has 3 jobs: get it in the muscle cell, get it from the muscle cell to the mitochondria, and then use it in the mitochondria to make ATP. There's no math this time, so I thought you might like that. So in order to get oxygen into the muscle, we need more capillaries. More capillaries equals more oxygen in the muscle, because there's more doors for oxygen to travel. But once it gets in there, we have to actually get it to the myoglobin, or get it to the mitochondria, and this is where myoglobin comes in. I believe I've used this analogy in class. Like, just imagine if my 4-year-old was in class, and assuming he was comfortable not being his typical initial shy self, once he feels comfortable, he's just going to be all over the place running around. Okay, but if there's like a specific place that I need him to go, I'm probably going to have to lead him by the hand. That's kind of what myoglobin does with oxygen. And then finally, I have to use that oxygen in the mitochondria to make ATP. Mitochondria are factories, okay, that generate ATP, but in order for them to generate ATP, they need oxygen. So if I have more mitochondria, I can use more oxygen. I can use that more oxygen to make more ATP. And in order to facilitate this, I need the oxidative enzymes that basically allow oxygen to be used to create ATP. So the limitations are several. We got to get it in. So do we have enough capillaries? We have to get it to the mitochondria. So do we have enough myoglobin? And then do we have enough mitochondria to take advantage of the oxygen we do bring in? So do we have enough mitochondria? Do we have large enough mitochondria? And then also, do we have the enzymes that allow us to go through all the steps so that oxygen can be used? So when it comes to aerobic endurance, there's 3 systems, and they all are limiting factors at different types of athletes. So if you're sedentary, or in a sedentary person, cardiac output will be more than enough. Respiratory system is going to bring more than enough oxygen in. It's just your muscles aren't able to use it. So with a sedentary athlete, it's going to be the muscular system. With a trained athlete, and this is kind of how I feel right now, I just got back from an 8-mile run at midnight, so there you go. I did have my lights on, so that was a little, so I was safe there. So I'm a trained individual. My cardiac output probably isn't delivering enough oxygen to my muscles, or that as much oxygen as my muscles could use. And this is likely due to stroke volume just being maxed out. So those are the primary limitations. And then an elite runner, and this here is a guy from BYU he won the last 2 national championships. I think the last time he lost a race was when the national championships were here in Terre Haute in 2009 19, I think it was. So it's possible that his limitation is the respiratory system, because just his cardiac output's so high that there's low transit time. Maybe he's got increased shunting. Remember, those intrapulmonary shunts are open during exercise as a pressure relief valve. There could be respiratory steal, and it's possible he's just not breathing enough. That is also something that happens, but very rarely. So there you go. Can you do the two things, which are explain how these systems can limit VO2 max and explain what kind of athlete has what kind of limitation?